Morning, everyone. I guess lecture for you today. Today we're going to cover differentiation formula, section 2.3 in Stewart. So as we saw in discussion yesterday, we want to recall, like, what is our definition of differentiation, right? So our definitions here. Differentiation. We've got two of them. Right. So f prime of x equals a limit as h approaches 0. And then what's my top? Someone tell me. If I do h approaching 0. Yeah,
X plus h minus f of x.
Perfect. Yeah, so f of x plus h minus f of x. And then we put that all over h. So that's one of our definitions. And then another alternate one is if I do f prime of a, I can do the limit as x approaches a of f of x minus f of a all over x minus a. Right, so we're doing sort of a slope thing in either case. But as we saw yesterday in discussion, was the homework, these take quite a bit of computation. And so, you know, these are quite, I would say, quite tedious, I would say, these to actually work with. Right. And so today's goal is actually to make some formulas to make this all easier, okay? Find some formulas to make this easier and faster. So the first formula we're going to think about is what if we have constant functions? So I'm just going to suppose I have f of x equals some constants. So what do these functions look like? What do the graphs look like? This horizontal straight line, exactly, right? And so they're going to look something like this at some value c. And so we got to think also the taking the derivative is a slope. And so what is the slope of this line? 0. It's a slope 0, right? So we should, no matter what c we have, hopefully get 0. We can actually compute this and actually put this into our formulas. So if I actually, sorry, not my formula, my definition. If I do f prime of x equal to the limit as h approaches 0 of f of x plus h minus f of x over h. Right, but f of x plus h in this case, if I plug x plus h into my function, what is it going to spit out? C. It's always going to spit out c. So this is the limit as h approaches 0 of c, and then minus f of x, also c, all over h. Right. That's c minus c. That's going to be 0. We have the limit as h approaches 0. Sorry, yeah, h approaches 0 of 0, and that's 0. So we see from our definition that it does actually work out. Yeah. Question, Charlie?
Yeah, something I'm wondering there is, so in like previous examples we looked at, the h in the denominator will factor out. So when you're taking that, it's like it's kind of clean, it's conceptually clean to say what this value is.
Yeah.
So here, I guess 0 is the numerator, so it's kind of intuitive for that reason that it should be a 0, but still sort of wondering, I guess I'm still have to hang up on there being a like a zero in the denominator, is that like a problem? I guess, or is it maybe not a problem, but the zeros in the numerator, and therefore it's still zero?
Yeah, you're exactly right. So yeah, the issue here, so we get a 0 over an h. And so you would be concerned that the h is still in the denominator, but because we already have the 0 in the numerator before we take h towards 0, that's all still 0 the whole time. Yeah, so the great question. Okay, any other questions? Okay. Yeah, all right. Right, so this works for any constant function. And so I'm going to add a little bit of notation that shows up here. So side note on notation is we're going to use this d over dx to sort of signify a derivative. It's a slightly different notation. It just means the same thing as f prime of f of x, right? And you can think of it coming from the, this sort of comes from a change in the y over a change in x, which is our slope, right? So this is taking the derivative with respect to x, but that's sort of where it comes from in some sense, okay? So using this new notation, I actually get the formula that d dx of any constant function, c, equals 0. So that's our first formula of the day. Anytime you see a constant, you want to take a derivative of it, it's going to be 0. Okay. So the next one we're going to look at is we're going to look at power functions. So what I mean by a power function is something of the form x to the n, where our n is going to be a natural number. Okay. So to find this formula, I'm again going to go back to the definition, but this time I'm going to use, recall that I had two different definitions, one with the h and one where I'm just taking a slope between some fixed a point and an x that's approaching it. We're actually going to use the second one just because it's a little bit more computationally easy in this case. So we're going to figure out what f prime of a is. So using my definition, the limit as x approaches a of f of x minus f of a over x minus a. Okay, so we're going to put in this our function x to the n here. So we're going to get x to the n minus, oh, not that one. Plug in an a, so an a to the n, x to the n minus a to the n, and then divide that by x minus a. Okay. So at this point, it might look like we can't do anything, but there is a way to factor our difference here, x to the n minus a to the n. If you've seen like difference of squares and how those factor, this is very similar, but this is the more general case. So I can factor out an x minus a, and then what's remaining is x to the n minus 1 plus an x to the n minus 2 times an a plus, and then so on. Keep repeating that pattern, taking one off x and putting it onto a, until we get x times a to the n minus 2 plus an a to the n minus 1. And that's still all going to be over x minus a. One of the sort of quickest ways to see this is to actually do the expansion. If you expand out, expand out all your x's to all of these terms, and then expand all your a's to all of these terms, then you'll actually get that you have a lot of cancellation, and the only things that are left are sort of the x's at the very beginning, that x times x to the n minus 1, and then the minus a times that a to the n minus 1. Everybody else. So it does actually work out for the general case. And then we can see here, I've got an x minus a factor on the top and on bottom. Those are going to cancel each other. And so I have the limit as x approaches a of x to the n minus 1 plus an x to the n minus 2 times a plus and so on times x to the a to the n minus 2 plus a to the n minus 1. Okay. So now we have a nice polynomial. We don't have our denominator anymore. So now we can just substitute in the a here, a nice continuous function. So we get a to the n minus 1 for the first term. And then for the second term, you can see I have 2 minus a to the n minus 2 times another a, which turns out to be another a to the n minus 1, and so on. And all these turn into a to the n minus 1, all of them. But it turns out that I have n of these. I have n copies of those. So I can combine my like terms and I get n to the a to the n minus 1. No matter what n is. Yeah.
Oh, that's special on the.
The factorization?
Yeah.
Not know if there's such a good information. Yeah, it's just the how that one factors. So like when it's squares, I know it's called difference of squares. But I don't know that the general form has to. Yeah, so you know, expected to know how it derives. That's up to Professor Grant for sure, but I would guessing that, I mean, part of this is that we're doing the derivation so that then we have the formulas and it's nice and easy to use. So most of the time when you're doing the power rule, you're just applying the rule and doing it. Yeah. Great questions. Okay. Right, and so just to make sure we have this very clearly, our formula for the power rule here is that if I have just some x to the n, and I want to take the derivative of it, I pull the power down as a coefficient, and then I drop the power 1 degree. And this, we only figured this out for when our power here is a natural number, because then we could use this factorization. All right, so that's our next one. Yeah, I don't. Constant function. Yeah, so we've done constant functions and now we've done power. So our next one we're going to do here is a constant multiple. And so by this, what I mean is, let's say I have some function g of x, which is, I know is some constant multiple of some other function f of x, and I know the derivative of f of x. How can I then get g of x, the derivative there? Okay. So how do you think we're going to do this? We're going to go back to the definition, of course. Let's see what happens. So g prime of x equals the limit as h approaches 0 of our g of x plus h minus g of x all over h. Okay, so g of x plus h in this case. All right, my function is c times f of x. So that's going to look like c times f of x plus h. And then g of x is going to be c times f of x, still all over h. So what simplification can we do here? Anyone want to help me out on what maybe we could do that numerator? Take out the C, factor out the C, exactly. Right, so I can factor out the C and get f of x plus h minus f of x all over h with a C on the side. But because this is a constant value, I can actually pull that all the way out. I've got limit laws that tell me I can pull it all the way out of the limit. Right, so it's C times the limit of f of x plus h minus f of x all over h. Right, so that's limit laws that allow me to do that. All right. Now looking at this, I've got this whole limit of f of x minus f of x over h. And that, of course, that is just our definition of f prime of x. And so we get that g prime of x equals c times f prime. And so that's our next formula. So if I have a constant multiple that I'm taking derivative of, constant multiple of a function, I can pull that constant out. So let's now put some of these formulas, now that we have a couple, into practice. All right, so let's try to figure out the derivative of 3x to the fourth. Okay. But this time we don't have to use the formal definition. We're going to use our formulas that we've come up with. So what's the first one that I can use? So we definitely have a power in here, but I can't quite use them yet. Don't look exactly like x to the n. Before we use power, yes, exactly. Constant multiple, we're going to use constant multiple and pull out that 3. Right, so that was using constant multiple. To pull that one out. Okay, so now I have 3 times the derivative of x to the fourth, and now, because I have x to the fourth, now we can use power. Now's our chance to use power. So using power, what is that derivative of x to the fourth? 4x cubed. Okay, so that was using power. And then we can simplify it just a little bit. We got 3 times 4, multiply those coefficients to get 12x. Right. So, vote. Do we like formulas better than doing the definitions by hand? Yeah. It's good to know them, yeah, because that's how we get these formulas, but this is really going to be an advantage going forwards. Okay. Any questions? Yeah. So when we did the power rule, yeah, so we have to use the constant multiple, because when we did the power rule, really all we figured out was that something that looks exactly like x to the n has this derivative. Because if I were to go back to when we did this, if I had a three running around here, I'd have to. Okay, yeah, you could at this point also do it with a C and factor out the C first, but that's just, you basically split it into two parts. Yeah, yeah. Excellent. Any other questions? Okay. So next thing we're going to do, we're going to do sums and differences. Okay, so let's say I have some function k, which is actually made up of the sum of two functions f and g. Okay, so using our definition, again, k prime of x is going to be the limit as h approaches 0 of k of x plus h minus k of x all over h. All right, we're going to substitute in, if I have k of x plus h, really I can take that x plus h and put that into both f and g and then add those. So we're going to get f of x plus h plus g of x plus h. That's k of x plus h, and then minus f of x plus g of x. That'd be all of it. Okay. So the next step in simplifying this is I'm going to distribute that negative to both of those terms and do a little bit of rearranging. So I have an f of x plus h minus f of x, and then I'll have a g of x plus h minus a g of x, and then I can split up, put both of those over h. The limit of that whole quantity. Now, since I know that the limit, assuming that f and g are both differentiable, I know the limit of each of those exists, and so I can actually split up the limits. I'll take the limit of f of x plus h minus f of x over h, and then plus the limit as h approaches 0 of g of x plus h minus g of x over h. So that first one, what does he look like? This first one, the definition of what? Yeah. Of what function? That's what I'm trying to get at. What's the name of the function that I've got? The first. Yeah, so that's the definition of f. So this is a definition of f prime of x. And then the second one. G, yeah, g prime of x. Right, so it turns out if I have a function that's made up of two functions added together, I can just take the derivative of each one. So that's our next formula here. Right. If I'm taking the derivative of sum of functions, I can just take the derivative of each one separately and then add them. Okay. Box that guy. Now, to do the sum, or not the sum, we did the sum. To do the difference, right, let's say I have f of x minus g of x. We can either go through the whole process again, it'd be pretty tedious, or I can notice that this is f of x plus a -1 times the g of x. Use the sum plus my constant multiple, and so we can actually get that for differences, we have sort of a similar thing going on. If I have f of x minus g of x and I'm taking the derivative of it, then I have d dx of f minus d dx of g. Okay, so differences also work. I want to do another quick example with this, just to see how we put this one into practice. Let's say I'm going to take the derivative of x to the 8th plus 10x cubed minus 6x plus 5. Okay. So I can use the sums and differences. I can use them repeatedly, and I'm going to break it all up into each term here. So dx of x to the 8th plus dx of 10x cubed. Now let's do minus ddx of 6x, and then plus ddx of 5. Okay, so ddx of x to the 8th by our 8x to the 7th, great. And then ddx of 10x cubed, 30x squared, right, using the constant multiplying the power. ddx of 6x. Yep, so minus a 6, and then ddx of 5 is 0. Oh, one thing I want to point out. Okay, with 6x is you can think of it as a 6x to the 1, and so you can still use power rule on it. Yeah. So, okay, yeah, you can still use power rule, and so what you get is you actually get like a 6x to the 0, but x to the 0 is anything to the 0th power is 1. So that actually doesn't change anything. Okay. All right. Excellent. Any other questions on this? Okay. All right. So we did addition, we did subtraction. Now let's do products. All right, so suppose I have some k of x, which is f of x times g of x, right? So first sort of thing I want us to think about is, you know, if I have two functions multiply together, f times g, and take the derivative, is this just going to be like the sums where I just, take the derivative of each part separately and multiply them together? Okay. Let's think through an example, a really simple example to think through this. So let's suppose my f of x is just going to be x, and g of x is going to be x squared. Okay. Then if I think about like what f times g prime is, well, x times x squared is going to get me x cubed prime. All right, I'm taking the derivative of that, which by power rule, I know is going to be 3x squared. But if I take f prime times a g prime, that's going to be x, the derivative of x, times the derivative of x squared. Right. Derivative of x is going to be 1. Derivative of x squared is going to be 2x. So that actually gives me 2x. So you can see, right, are those the same? No. Okay. Right, and so we're actually it's gonna be a little bit more involved for product rule. Okay. So let's go back to our definition here. Also, if I go too fast, please tell me to stop, because you still are talking. Okay. So definition, again, k prime of x. The limit as h approaches 0. K of x plus h minus k of x over h. And then we know that k of x, because we're doing product rule, it's going to be a product there, f times g. And so this is going to be the limit as h approaches 0 of f of x plus h times g of x plus h minus f of x times g of x. And that's all over h. Okay. So we need to figure out a way to sort of pull the derivatives of f and g definitions out of here. And this is one of my favorite tricks in mathematics, is we're going to add a funny 0 to make this work out. So the funny 0 that I'm going to add, first I'm going to just recopy my f of x plus h times g of x plus h. The funny 0 I'm going to add is going to be minus f of x plus h times a g of x plus an f of x plus h times g of x. And I still have my minus f of x, g of x. And that is all over h, right? So you can see that these two terms that I've added in the middle, those are actually just equal to 0. So I haven't changed the value here. I've just added a 0. And the reason I did that is because if you look at the first two terms, right, these first two terms, I have an f of x plus h in both of those. So I'm going to actually factor that out. Oh, and I'm still on pink. Right, and then what I'm left with is a g of x plus h minus g of x all over h there. And then from the second two terms, you can see that I have a g of x in both of those. So I'm going to factor a g of x out of that. And then I'm left with f of x plus h minus f of x all over h. So now I can split up my limit. Take the limit of f of x plus h times the limit of g of x plus h minus g of x all over h plus a limit of g of x times a limit of f of x plus h minus f of x over h. Right. And now I see I've got the definition of g prime and h prime in there. And then as I sort of, for the first one, f of x plus h, as I send h to 0, that's going to get closer and closer to f of x since that's continuous. And so we really get f of x times a g prime of x plus g of x times an f prime of x. So that's how we take the derivative of a product. Our final formula is the derivative of f of x times g of x is f of x times the derivative of g of x plus g of x times the derivative of f of x. And so I want to just do a, circle back to our example here earlier where we had, f of x equal to x and g of x equal to x squared, and actually use our new product rule and see what we get. Right. So using this product rule, we have x times x squared prime. You can think of being split up like that. And so I get first I have my function f. So that's going to be just x. And then I take the derivative of x squared. And then I add my x squared times my derivative of x. So that's using product rule. And so what I get here is I've got x times, using my power rule, 2x plus x squared times the derivative of x, which is 1. And so we get 2x squared plus an x squared, which does give us 3x squared, which is the derivative of x cubed using power rule. So it checks out, it works. All right. Any questions? Okay. All right. Oh, I was for some reason thinking we stopped in 10:50. We don't. We have more time. Excellent. Okay. So we did product rule. Now we did addition, subtraction, multiplication. Next one is division. Now we're going to do quotient rule. Okay, so suppose I have a function k of x, which is some f of x divided by g of x. We're going to dive straight into the definition. So this is going to be limit as h approaches 0, k of x plus h minus k of x divided by h. And using what I know, k of x is, we're going to get limit as h approaches 0, f of x plus h divided by g of x plus h minus f of x over g of x, and then divide the whole thing by h. So we have a pretty messy fraction to deal with, complex fraction. Right. There's sort of two ways to tackle it. I could combine the top to get a single fraction. Or another option that I'm going to do is I'm actually going to multiply both the top and the bottom of my big fraction by all of the denominators, factors the denominators that I see. So basically by my g of x plus h times g of x. And I'm going to do that on top and bottom. So what happens is when I distribute that out in my first term, my g of x plus h's are going to cancel, but I'm left with f of x plus h times g of x. And then in my second term there, the g of x's are going to cancel, but then I have the g of x plus h. So I have minus an f of x times g of x plus h. And then it's going to be all over h times g of x plus h times the g of x. Okay. So again, I have these two terms that I can't quite pull apart. A derivative of f and a derivative of g. So again, I'm going to do this adding a funny zero in. In this case, what my funny zero is going to look like is f of x times g of x, adding and subtracting that. I'm going to add and subtract that term, and then I still have my minus f of x, g of x plus h. So again, very similar to product rule. You can see I've got an extra g of x in the first two terms. I'm going to factor that out. I have an f of x plus h minus an f of x. I'm actually going to pull the h up from the denominator as well to there. And then in my second two terms, you can see I have an f of x in common. Okay, there we go. Now you may notice I was looking at this, I have a positive g of x and a negative g of x plus h, and I'm going to fix this by, instead of pulling out just a positive f of x, I'm going to actually pull out a negative f of x. Yeah. So that then what I'm left with is I'm going to end up with a positive g of x plus h minus a g of x, and then over my h again. And then in the denominator, I still have g of x plus h times g of x. Right. Now that we have that, all of these parts that we have now broken it down into, we can get limits of. And so we are going to break up all of our limits. g of x, take the limit of this f of x plus h minus f of x for h minus limit of f of x, a limit of g of x plus h minus g of x over h, and divide that by a limit of our denominator, the g of x plus h times g of x. Okay. And now we can see by taking the limits, we get g of x times our f prime of x minus an f of x times a g prime of x divided by a g of x squared. So that is going to be our quotient rule. If I have some division of two functions, it'll be g of x times the derivative of our top function, subtracting the top function times the derivative of the bottom function, all over the bottom function squared. So that's quite a messy formula, but it's certainly easier than trying to remember all the tricks that went into the actual computation of the definition. And I have a great story with this one. When I was first taking calculus, we came across this one, and my calc teacher, we were all like, how are we ever going to remember this? And he was like, go home, say it 100 times before the next class, you'll remember it. So I mean, that was his hint on how to remember it. The way that I usually remember it now is I have like a general idea, and then I remember that the subtraction always goes when I'm taking the derivative of the denominator, because denominators have negative exponents. That's how I remember it. Okay. All right. We are nearly out of time. Let's just use this in a quick example here to get a little bit of practice with this. All right, so let's suppose I have f of x equals x squared plus x minus 2 over x cubed plus 6. Okay. So you can see that my top function, nice polynomial there. Bottom function, also nice polynomial. But to actually like compute this with the definition would be a huge algebraic nightmare. So we don't want to do that. Let's use our quotient rule. So f prime of x. So first we're going to take the denominator. That's just x cubed plus 6. And then we're going to take the derivative of the numerator, x squared plus x minus 2, take the derivative of that, and then subtract the numerator, x squared plus x minus 2, times the derivative of the denominator, so x cubed plus 6 prime, and then put that all over the denominator squared, x cubed plus 6 squared. Okay. All right, so now we're going to do the derivatives here. X cubed plus 6 times the derivative of x squared plus x minus 2. Going to be 2x plus 1. And then minus our x squared plus x minus 2. And the derivative of x cubed plus 6. Going to be a 3x squared. all over an x cubed plus 6 squared. So if we wanted to, we could expand this all out and simplify. I don't know what Professor Brandt's policy is going to be on the test. I know last semester, this is what we wanted to see, because then we can see if you actually know quotient rule, but. All right. Any final questions? Yeah. This is now just output, so just FOIL. Okay, so Caitlin's question, which is great, is do you do a product going out with a product there? And so there's no derivative left here, so you just FOIL. Great question. Anyways, thank you for coming to class. Have an awesome weekend.
That's happened to me before. I had a class that was like